very much. Thank you very much for the invitation and for this kind introduction. And as you mentioned, I'm going to discuss the g-2 from the lattice and experiments and try to answer the question or give a little bit of a clarification if we had 4.2 sigma. As you mentioned, this is done in collaboration with the Budapest Marseille Wuppertal group. Some people call us BMW. It's about 10 to 12 people. Lattice collaborations tend to be even larger than that. Probably many of you have heard that on the April 7th last year, 9 months ago, the Fermilab experimental group announced a new result on the muon's magnetic moment. And on the same day, on the very same day, Nature published our theoretical calculation for that. And since we will discuss the discrepancy between these two, the theory and the experiment, I should say that both of them are equally important if we wanted to get some new physics. So it was everywhere in the press, from the Frankfurter Allgemeine Zeitung to Forbes magazine, from Wall Street Journal to Le Monde, from Yahoo News to New York Times. New York Times had it on the opening page for 2 weeks, which is quite rare in science. And even more at the end of the year, it became one of the 10 breakthroughs of the year in science, one of the 2 physics breakthroughs. And they claim that on the same day experimenters released their results, one team of theorists published a calculation that they argued increases the standard model prediction and closes the observed gap. And actually, just in the most recent issue of the CERN Courier, Ed Witten, when he was speculating where should particle physics go or what should we do, he said that the dream to get a concrete clue about what is the energy scale for new physics is very important to improve the lattice gauge theory estimates of the hadronic contribution to the muon. And that's what I'm going to do now. The most important picture which I want you to bring home is this one. This is the magnetic moment of the muon, actually just the 8th and the 9th digits here on this axis. The experimental result was this Fermilab red dot with its error bar. This is the 20 years old Brookhaven result. And if you average them, then you have this purple band as an experimental average. On the other hand, there is the so-called white paper, which was written by 134 people or so, and it included all the standard model contributions, theoretical contributions to the muon's magnetic moment. And as you see, there are 4.2 sigma discrepancy between the experimental average and the white paper result. White paper or dispersion relation or R ratio or data-driven method, I will use all these expressions to refer to this green band. And our lattice result, which is not data-driven, so it's not including all the E plus E minus data sets of the last decades, but this is just a pure theoretical calculation on the lattice, which is the first one with comparable errors, fully overlaps with the Fermilab result. The tension between the experimental findings and the BMW lattice result is just 1.5 sigma, which is no worry at all. So this is something which you might believe or might not, because you have heard for 35 years that the lattice is solving this problem and that problem, and I don't know how much you have seen, but this slide shows just from our group what can be done with the lattice. The first figure shows the order of the quantum chromodynamics transition predicted by the standard model of particle physics. Nature gave this long title of that, but it tells us that the QCD transition was actually a crossover and not a real phase transition. So there is no need to look for remnants related to a first order phase transition. Or another calculation here, this is the Hadron spectrum. Sorry, this is the Hadron spectrum. This is the Hadron spectrum of a dozen or so particles, and the horizontal lines are the experimental values, the bands are the widths of those states, and the red dots with their error bars are the QCD prediction based on lattice. And as you see, everything is lying as it should be.
Sorry, you don't mean the bands or the widths and the, right, the lambda is practically, it only decays weekly, and so its width isn't in the MEV range.
Yeah, it's
essentially
not visible here, yeah. But the
Oh,
delta or
I'm sorry, I was misreading the thing. Okay. But so
yeah.
It would be more interesting if you blew it up so we could actually see the comparison with the error bars. But anyway, you're telling us that they're all within 1 sigma?
Well, all within 1 sigma, yeah.
Okay.
Actually, yes. Yeah. Which is perhaps means that the errors are perhaps a little bit overestimated, but they are of course correlated, yeah, because they have the same propagators. So the rho has the same propagators as the nucleon, and the case.
Excuse me, what about excited states of these hadrons? Do you claim that you can see on the lattice Regge trajectory or Regge-like trajectory?
Yeah, that's a very interesting question. So in this paper, which was also a breakthrough of the year in 2008, we just wanted to have the lowest lying hadron spectrum. And what you see here is, for instance, that the omega has a very tiny error, or lambda. And it is related, it is related to the fact that it is always hard to calculate something which is from light quarks. So the delta is built up from light quarks. Light quarks are hard on the lattice. Baryons are harder than mesons. Decaying particles are harder than non-decaying or stable particles. And that's why the delta has a huge error, whereas the omega has a tiny error. The nucleon has a larger error than the lambda because it is only light quarks. And the rho has a larger error despite the fact that it is a meson, because it is decaying, and that's a problem. So these errors roughly reflect the difficulty in the lattice calculation, but that was a very.
What about the eta and the eta prime? They don't decay at this scale, so they would be a.
We didn't calculate those ones.
Oh, shame on you. Those would be hard.
Yeah, they are hard. So these are.
I mean, it's a little cheating to do only the easy ones and then use it as a testimonial to your the quality.
Beg your pardon?
I'm just telling you, for us, it's these comparisons that let us know how good your calculations are. And so you shouldn't just restrict to the easier ones. You should do the ones that where you might not be able to get it right. So one can better gauge if there's a, how reliable they are. That's all I'm saying. So clearly the eta and eta prime would be key to get the physics right, since it involves the, the U1 problem and so on. Anyway, I'll let you give your talk, but just for the future, you might.
Yeah, I'm fine with your opinion that would be also nice. That's what we did. Mm-hmm. Nothing more, nothing less, and I didn't claim anything else. What we did too is to calculate the isospin mass splittings, which is 1.4 MeV or 1.3 MeV, and compared to these 1,000 MeVs, yeah, it's 3 orders of magnitude smaller. And here they are, the isospin splittings in the various channels. And you can say that calculating these quantities are easy because you know them experimentally. Here I show you with these blue shaded regions, which are experimentally not known or not known as well as we did. So these are predictions. Or another thing which we calculated is, for instance, the equation of state in the early universe for 5 orders of magnitude. So all what I wanted to illustrate with these slides is that Lattice really has reached a level where quantitative statements can be done. If you believe it or not, that's up to you. So this is the outline of my talk. First, I will very shortly speak about the g-2, and then I simply go through the purple band, the green band, and most importantly, the gray band, and finally I summarize. So as you all know, the muon is a subatomic particle discovered in 1936, the cosmic ray. It has the same electric charge, the same spin as the electron, but it's 207 times heavier. And it has a finite lifetime of 2.2 microseconds. And the question is how strong this magnet is. If you put some charge top with a homogeneous charge and mass distribution, you will have a magnetic moment. And the magnetic moment can be this 2, which we discussed before the talk, but usually we call it G. In relativistic quantum mechanics, it's 2, but in reality, there is a 1 per mil correction to that, and that's what I'm going to discuss. And whenever you see this quantity A, it means g-2 divided by 2. So this is the half of this anomalous part. So let me come to the experiments. I'm not an experimentalist, but perhaps it's worth to say a few words on the experiment. So the newly announced result at Fermilab is shown here. On the last digit, we have an error of 5.4, and it's written in units of 10 to the minus 10. And I will use these units in many cases in the talk. It is such a sensitive experiment that it is similar to see weight of a single eyelash on a bathroom scale. The Brookhaven result 20 years ago was slightly worse, just a little bit worse from the error point of view. And if you combine them, you have a 4.1 error in the last digit, and the target uncertainty is 1.6. So we will still have a much better accuracy from the experimental point of view. So this is a history of the g-2 experiments for the muon. Some of them are mu minus, most of them are mu plus, and these are the errors. And as you see, the errors are decreasing rapidly to reach the last BNR result of 6.3. As you probably know very well, Brookhaven had these 30 million magnet, but they didn't have enough muons. That's why this error was statistics limited. And Fermilab had the most intense muon beam in the world. So the idea was to bring these large magnet to Fermilab from Brookhaven. So here is Brookhaven, here is Fermilab. It was impossible to do that on the freeway because it's huge, 4.5 lanes. So they put it onto a boat and sailed down the East Coast and then back on the Mississippi River.
Was the shipping cost much cheaper than 30 million?
What's that?
Was the shipping cost much cheaper than 30 million?
I think so. I think so. And I think also that's a question of time too. So if you want to get a big magnet of that quality, it takes much more to to make it, much more time to make it than to ship it. But I think it was an order of magnitude, at least an order of magnitude cheaper.
Also supply chain.
So here are a few pictures of this big move. It was not allowed to bend this 14-meter magnet more than 1 millimeter on the whole thing. So here, when it was put down, here is St. Louis on the way to Fermilab, and here is the cheering crowd when the magnet arrived. So here is the storage ring at Fermilab. Here you see the detectors all around, 14 meter, 1.45 Tesla, and the momentum of the muon is about 3 GeV. So what it does, it has a cyclotron frequency and it has a spin precession frequency. And the difference between them is proportional to a mu. So what you're doing, you are injecting the muon. There is this cyclotron motion around, and the precession frequency is a little bit larger. That means that it goes a little bit faster around than the momentum itself. And if you measure how fast this is rotating compared to the momentum, then you actually measure the mu. And that's what they are doing. So first, proton producing pion. Pions are decaying, producing mu plus. And in the storage ring, mu plus is decaying into E plus. But there is a strong correlation between the mu plus spin and the E plus momentum. So if you're looking at these detectors, you're just detecting the direction of the spin, and the direction of the spin is rotating with the frequency of a mu. So once you have detected that, then you measure this frequency, and from that frequency, you have a mu. So that's more or less the experiment, how it is done. Let me move on to the white paper and the standard model prediction based on the data-driven technique. So in the standard model, we have all these virtual particles around the muon coming from QED, coming from the electroweak, and coming from the strong sector. And the white paper with over 130 physicists collected all these results and even calculated many of them. So here are the individual contributions. QED is far the largest, but interestingly, there is 0 error on it. The electroweak is quite small, almost 0 error. And the strong one is between the electroweak and the QED, and all the error is coming from the strong one. So if you want to make a comparison between experiment and prediction, theory prediction, more sensitive, then the only way you can do that is to reduce the error on the strong contribution. QED is a very nicely and rapidly converging series, and it was a key to success of QED. So here you have all the contributions. This is 1 loop, 2 loop, 3 loop, 4 loop, 5 loop, and that's the total result. And here you see the 3 level, the 1 loop, 2 loop, and all these diagrams. Kinoshita calculated, and collaborators, the 5 loop. It was 12,672 diagrams. Of course, it is not generated by hand, but it is automated generation, numerical evolution, only some diagrams known analytically. And it has not yet confirmed by other groups, but it doesn't matter because it is so small, the contribution, that even if it had a problem, it doesn't contribute to the final result on the error budget.
Can I ask you
question
Sure.
to follow? At what scale the alpha corrections are taken, QED or QCD later?
That's a good question. I would say that here is probably the muon is the dominant scale, and I would say that there is not too much running from the Thomson limit to the muon scale. But to be honest, I do not know the exact answer for that. So that was much more of a guess than my knowledge.
Yeah. For QED, I wouldn't worry, but for QCD, probably I would.
Oh, for QCD, I will discuss that. I will discuss that. Yeah,
Okay.
I will discuss that. Yeah. So that's why I said for QED, I wouldn't worry too much either.
Got it.
So let me come to the QCD.
Excuse me, a short question. Do you know if people try to modify QED by taking nonlinear QED, this DBI action, and see what kind of changes it could have produced?
So some modification of QED to cover the discrepancy between these two things. That's what you're asking.
Right,
so
right.
Between that and that.
Mm-hmm.
To be honest, I don't know all the papers. There are, I think, over 500 papers now who are trying to explain this discrepancy. Just on the next day, when the experimental paper and our paper came out, there were dozens of, I think, something like 40 papers. So I can imagine that somebody had this idea and tried to.
Since the contribution of QED is the major one, it would make sense to try and.
Yeah, that would be very easy to make a small contribution there. Exactly. That's a good idea.
Mm-hmm.
So here we see that here you just do something in these last two digits, and then you already have an agreement. Of course, it is not easy to have something as a new model. I'm not a model builder. When the discrepancy is 25, yeah, and the electroweak contribution is 15. So it's not easy because it must be twice as large as the electroweak contribution.
Mm-hmm.
Anyhow, in QCD, we have leading order hadron vacuum polarization. This is the graph for that. We have next to leading order vacuum polarization, and we have the hadronic light by light. For a long time, the hadronic light by light was considered to be the hard case and the most difficult to handle. And it is still difficult to handle, but the dominant error is not coming from here. So it has a relatively small error. Phenomenology and lattice do agree with each other. There are actually two lattice results on that. So the big error is coming from this graph, and that will be the focus of my talk. So this is the hadron vacuum polarization, and obviously alpha S is large, so you cannot do the same thing what you were able to do in QED. Instead of that, people are using the so-called R ratio and the optical theorem. So this vacuum polarization, the hadronic vacuum polarization, can be related to the total cross-section. And the total cross-section data on E plus E minus. So E plus E minus going to gamma, gamma goes to hadron. We have decades of data. Here are a few experiments. And here is this R ratio, which we teach to the students in 5th semester or so. It has a lot of structure, of course, J psi and epsilon and the Z pole. And what you do is you take this R ratio, there is a kernel function, you multiply them, integrate them, and that's the contribution to the magnetic moment of the muon. And in the literature, there are many people who has done that. and they are all around 690 or something like that. But the discrepancy between theory and experiment, as I said, is 25. And that brings these 4.2 sigma significance between the two results. And the error budget is shown here. So 4.1 is coming from the experiment. That's what we discussed already. And 4 is coming from HVP. So this is the dominant error right now. And that's the task to push down. As I said, it's huge. It's almost twice as the electroweak contribution. So we might want to speculate. So what do we need for new physics? What we need is Fermilab really reducing the error to 1.6. So instead of 4.1 here, we will have 1.6. And if the theory error remains the same, then it will be a 6 sigma discrepancy, assuming that the center value remains the same too. 6 sigma, it is more than 5, so all the journalists can be happy that we found signal of a new interaction. Even better if the Fermilab plan is carried out, so they push it down to 1.6. And if we can push down the light by light contribution by some factor, and these we can push also by a factor of 2 or 3 down or 2.5, then we will have a 11 sigma discrepancy. And that would be something you cannot ignore. That's if you hope for new physics. If you hope for no new physics, then you need 4% larger HVP, hadronic vacuum polarization, to get 720. If it is possible or not, we will see. Or you should have 360% larger light by light contribution, which is very unlikely. The error of the light by light is much larger, much smaller than this value. So these are the possible options for the future. And that brings me to the lattice calculations. This is the main part of my talk. So what we do is we are calculating this integral on the lattice, which is numerically 4 billion dimension integral. If we look at our typical lattice size, it is 100,000 years for a laptop, but 1 year on a supercomputer like that. But it is still a lot of computer time. On the lattice, we put the gauge variables on the links and the fermionic variables on the side. Instead of the integral, we have a summation. And there are two very important limits, and I will come back to that. The infinite volume limit, you do it numerically or analytically, and the continuum limit, which means you need at least 3 different lattice spacings. As I show you, we have 6 different lattice spacings. And what you do then, you measure the current correlator and multiply it with a kernel function. Here is the current correlator with the kernel function. And as you see, at large distances, you have much more noise than for small distances. And once you integrated that, then you have a mu for the muon. A few words about the simulation setup. As I said, we had 6 lattice spacings. These are from 0.13 Fermi to 0.064 Fermi, which makes a controlled continuum limit extrapolation possible. The typical box size, what we have is 6 Fermi, though in one case we had an 11 Fermi in order to reduce the finite volume effects. Of course, you have to be smaller than the size of the proton, which is 1 Fermi. So these lattice spacings are in the proper ballpark. This plot shows the light quark mass on the horizontal axis and the strange quark mass on the vertical axis, normalized by their physical value. So 1, 1 means that this is the physical light quark mass, and this is the physical strange quark mass. And our simulation.
What do you mean by physical, given that they're confined? I mean, is that could you just say a little more about that?
Yeah, so we say that the quark masses are physical if the pion mass and the kaon mass and all those things are physical.
Okay.
Yeah? So that's probably not so easy to see. So this is the pion mass squared divided by the pion decay constant divided by the physical one. So if it is the same, then we say that it is the physical quark.
Sorry, thank you.
No, it's okay. Anytime, any question. And I apologize that I didn't clarify that in time. So what you see here is all our simulation points are scattered around the physical point. So we are not doing any chiral extrapolation or physical quark mass extrapolation. We are doing tuning the system within a few percent, 1 or 2% to the physical mass. And here are the lattice spacings, the sizes of the lattice and the number of configurations. As you see, the smaller the lattice spacing, the larger the number of configurations we needed. Actually, there were four huge challenges to reach this level of accuracy. One of them was the inclusion of QED, because if you want to have a sub% accuracy, then you have to include QED. Then another challenge is determining the lattice spacing itself, because it can destroy the whole calculation if it is determined wrongly. Then we had to fight with the noise, and the largest uncertainty came from finite volume effects. So let me go through all of these, just one slide on each, because I don't want to spend too much time on that. If you are interested in the details, you can find it in the paper. It's a long paper, over 130 pages. So first, I discussed the scale determination. The lattice spacing A enters into the A mu determination 2 points. First of all, the lattice spacing in physical units and the muon mass in physical units should be in coherence. And when we calculate the values for m pi and mk, you use the lattice spacing again. And the bottom line is that if you have an error on the scale, the error on A mu will be about twice as much. So you have to push down the error on the scale if you want to push down the error on A mu. So for the final result, we use the omega mass for the scale setting. The reason for that is it is experimentally very well known, to many digits. It has a very moderate MQ dependence. And even if it was cheating or not, I showed you that it can be very precisely determined on the lattice. For some other quantities, we use the so-called W0 scale setting, W0 scale setting. It also has a very moderate MQ dependence, can be precisely determined on the lattice, but this is a gauge flow in a fictitious fifth dimension, so there is no experimental value for that. So what we did, we determined the m omega times W0, which gives you the W0 value shown here. The second task was the noise reduction. And as always, the noise is increasing for this current correlator for large distances. So this was the data I showed you on a previous slide, and the result from 2017 is in red, and from 2020 it is blue. And as you see, there is a tremendous increase in the accuracy. And the reason for that is not computer time, because you cannot get a factor of 10 in computer time, then you need a factor of 100. And for that, you need to wait, I don't know, 20 years. It was the load mode averaging, the technique which used exact quark propagator in the infrared. It's an all-to-all quark propagator. And in the UV, we were using the stochastic, old-fashioned stochastic method. And in addition, there is a way to decrease the noise by replacing CT, the correlator, by upper and lower bounds, as shown here. So all in all, we were able to get a few per mil level of accuracy on each ensemble for these CT or K times CT.
Zoltan, I have a question about that slide. So you said the noise blows up for large T, for large time, but why is that precisely? Is it because some of the correlators vanish at large distances? Or, yeah, could you?
It's always like that large time separations, when you calculate the correlations, they are simply noisier because everything is fluctuating more. And there is a technique to know how to estimate how it gets worse and worse, and it goes somehow the mass differences. So for instance, a nucleon mass and the pion mass difference tells you how the error is increasing, the noise is increasing as you increase the distances. But as I said, this low mode averaging all-to-all propagator cured it a lot. The largest uncertainty in this calculation from 2017 was coming from the finite size effects. So our typical lattice size was 6 Fermi, and earlier model estimates gave about 2% finite volume effect from the 6 Fermi to the infinitely large box size. So what we did in order to reduce that 2%, we took our reference lattice, which was about 6 Fermi, and carried out the calculation on a big lattice at 11 Fermi. The details are again complicated because you have a pion tower and you have to reduce the splitting within the pion tower. But at the end of the day, we were able to calculate the difference between the big lattice and the reference lattice. And the difference was 18.1, again in 10 to the minus 10 units. So that's the lattice result. And then we performed analytical calculations next to leading order chiral perturbation theory, next to leading order chiral perturbation theory, MLRGS, HP. These are various effective field theory models. And obviously the lower order chi-PT is not a very good choice, but all the others are somehow agreeing in fairly good agreement with the lattice result. It's 18 plus minus 2 from the statistical and 1.4 from the continuum extrapolation point of view. So that means that we can use the lattice determination for this difference. And these models, which are getting better and better for large volumes, for the difference between the big volume and the infinitely big volume. And that gives for a remaining finite size effect an error of 0.1%. And we also had these isospin breaking effects. And we published this table with 1.5 dozen predictions with the connected light, strain, charm, disconnected, isospin breaking valence, isospin breaking C, mixed, strong isospin breaking, and so on and so forth. And the final result was 707. And you remember it was 693, the original data-driven method result. So that's our final result. And now the
Could I ask a question?
result.
A really naive question. So for isospin breaking, there's the mass difference, and then there's just the electromagnetic effect. But how do you actually put in the Coulomb effects in the lattice? Is it some sort of hybrid between perturbation theory for the Coulomb? And
How do we put what? How do we put what on the left?
how do you put electric charge? How's QED? I mean, this is just a super naive question. I'm not doubting you can do it.
Oh no, it's a very good question. You could have asked this question already when I was speaking about the.
I thought of it, but I figure you might explain it.
Isospin splitting in the Hadron spectrum. So there are various ways to do that. In the isospin splitting for the Hadron spectrum, we used a direct dynamical field simulation, and the U1 field was there on the lattice, and we were updating all the time the electromagnetic field. Here it is done slightly differently. That's why you see here valence and C effect. So there is a sort of reweighting technology in the work, and the strong isospin breaking is simply taking different masses. Again, in the paper where we calculated the isospin splitting of the spectrum, we really used different quark masses. Here we used an expansion in the quark masses, and the reason why we did it there differently than here is in this isospin splitting, where we all know the physical answer, it was not a question how precisely you can tell the mass difference between the proton and the neutron, because it is known by the PDG certainly better than we can do it on the lattice. So we just used a theoretically simple and appealing framework to do that. Here, it was everything about optimizing the computer time. So that's why we splitted the valence sector and the C sector, splitted the strong isospin breaking part in order to invest as little computer time as possible to the individual questions, but nevertheless have a final error, which are all on the somewhat similar level and do not destroy the error of the final result. But that was an important point.
And then you can test that method on the Hadron spectrum.
Oh yeah, oh yes, oh yes. And it worked perfectly, yeah. So here is the status, what we published with the no new physics scenario, lattice results, and the data-driven method. This is this discrepancy between the various data-driven calculations and the experimental finding. As you see, the lattice results are all agree with everything, yeah, because the error bars are too large, except for these sub% precision result of us. So this is a 0.8% accuracy. As I said, it is consistent with the Fermilab experiment. It is 2 sigma larger than the Davier et al. Result for the data-driven method, and 2.5 sigma larger than the Gashar-Vazee result, which has a little bit more aggressive error estimate. So that's the situation. And let me discuss now some theory, thoughts, what we think can be the reason, or how we check that it is not, because it is a very surprising result, or at least it was for us very surprising. So we expected something similar to the data-driven method because it is just QCD compared to QCD. So one such a point to discuss is the so-called window observable. Let me come back to my current correlator, which is the red line here. And as you see, it has large errors, as we discussed. But what happens if you multiply it with such a window function, which is between 0.4 Fermi and 1 Fermi? Then you have this blue line, which has no problem anymore with the signal over noise because the large t distances are cut out. It has no problem with the finite size effects because large distance is sensitive to finite size effects. And it has no problem with the lattice artifacts, cutoff effects, which appear at small distances because it is also cut out. So this is something which is very easy to determine on the lattice. I used to say that it is on the 1 to 2% of the whole project. So both computationally and manpower-wise. And here it is, what we have. And this is the lattice spacing. This is some unimproved operator. This is some improved operator. And this is the extrapolation to the continuum limit. There are 500,000 ways to extrapolate. You can leave out the coarse lattices and keep only the fine lattices. You can use various fit functions all the way to the continuum. So we had at the end of the day about 500,000 of those, and the center 68% gives us the error, and that's it. So this is the prediction for this window function for the light quarks in the isospin symmetric case. And this is the result of the R ratio. And at the beginning of the talk, I mentioned that there is a tension of 2.1 sigma between the R ratio and the lattice result. But in this window, the tension is much larger. It's 3.7 sigma. So 2.1 is not really a worry. I used to say to my students that if you have a 2.1 sigma effect, you might be invited to give a seminar, but you probably have to pay for your travel expenses on your own. 3.7 is much more worrisome. And as I said, this is easier to calculate, and a bunch of collaborations calculated it. Here is a list of them. This is again the window observable from the R ratio, from the data-driven method, and these are the lattice results. So interestingly, they are all above the data-driven result. Furthermore, you can have a problem that you are using an action and perhaps it is not the best chosen action. Our action is a staggered action. So we did a cross-check with an overlap action, which is the theoretically most beautiful, cleanest way to define QCD on the lattice. And this is what we have with the staggered as a function of the lattice spacing squared. And this is what we have with the overlap. So they give the same result. Overlap is, of course, much more expensive, so the error is also much larger. This calculation was done not on a 6 Fermi, but on a 3 Fermi lattice, again, because of cost reasons. But it shouldn't matter. So if you check to discretization on a 3 Fermi box or a 6 Fermi box, they should give the same thing in both cases. And let me show you the continuum limit, what we have here. So how we did it. So at a given lattice spacing, this is this black arrow. You calculate the A mu. Here I show you the A mu light. With various improvement of the operators for a coarse lattice, then you do that for the finer lattice, even finer lattice, even finer lattice, and then you can go all the way to the continuum, all the way to the continuum. And as I said, hundreds of thousands of ways to do that. It will give you a spread, and this spread is interpreted in our case as a continuum extrapolation error. And as of today, this is the dominant error in our calculation. And this brings me to my summary. So the final result is listed here. So all these contributions, and the most important message again, with our finding, this is the magnetic moment of the muon, the 8th and 9 digits. This is the most recent experimental result from Fermilab. This is from Brookhaven. This is the average result, 4.2 sigma with the data-driven method, but only 1.5 sigma with the lattice determination. And I thank you very much for your attention. And if you have further questions, I'm happy to answer them.
Maybe my two questions are, the improvement in lattice, was it only due to Moore's law, essentially, to have bigger computers, or say, if we compare to say 10 years ago, was also due to other advances? So that's, in a sense, a technical question. The second is, do I get it right that the main source of error in the data-driven model is the QCD contributions? So it's that where the uncertainty is, and not in the light-by-light contribution?
Okay, so let me answer both questions. So I would say that in the last 2.5 years, the improvement in computers was for us negative. So it was not the computer technology increase which improved our data from 2017 to 2020. We were using a blue gene computer in Jülich mostly, and it was shut down somewhat earlier than expected. And some of the calculations which were planned to run on that machine was impossible to do it. So we had a very hard time to finish the project because of these difficulties in the computer time. That means that many of these advances were not due to the computer technology, but much more lattice techniques which we have used here. As I said, the all-to-all propagators or pion tower reduction in the finite volume cases and all that. Your second question was, can you repeat it?
So where you have there is a big discrepancy between the lattice computations and the white paper, and do I understand it correctly that most of the uncertainty in the white paper computations come from QCD corrections, but not from the light-by-light data?
Yeah. So the light-by-light is suppressed by a factor of 100. Yeah. So this is 700 in 10 to the minus 10 units, and the other one is 9 or 10. Yeah. So it's a huge factor between them. And if you have a given accuracy on the 20% accuracy on the light by light, then the error is not the dominant error anymore. But if you have a 1% error on the vacuum polarization, then that would be the dominant error. So in that sense, the light by light is an important contribution. It has to be calculated, but the relative error is obviously much less important in that case. And the numerical values show that indeed the vacuum polarization has an error of 4 or 4.1, whereas the light by light has an error of 1.8. So it is not the dominant anymore. Did I answer your question?
Yes, thank you.
On both questions?
Both questions, thank you.
Okay, thank you.
And just to follow on that, it's a natural continuation what I wanted to ask. So you very nicely showed the origin of the difference between the white paper and your calculation, which is in the R ratio. I guess that I got that right. If I didn't, please tell me. And if I did, then the question would be, can you identify what would be a suspect in those data-driven calculations of the R ratio from your perspective? I understand that probably you cannot prove that this point or that point is wrong, but would be interesting to hear your thoughts. What may not be correct or exact in those calculations.
Mm-hmm. So I did that calculation on my own too, and I got the result. All the 5 digits of the result was the same, and all the 3 digits of the error was the same as this KNT data set. So I got from them the data set, I carried out this calculation, and I didn't see any error there. And
I have
let me finish that, yeah? And I even used this data set to calculate the data-driven result for the window function. So that's why I needed that. Having said that, it might be, of course, that the data set which I was using is in some sense underestimating the errors. For instance, the 2 most recent E plus E minus data set, which goes into this calculation, is Chloe and Babar. And in the most important region between 600 MeV and 900 MeV, they are 3 sigma away from each other. It is treated in a way in the white paper with a technology of error inflation, that's how they call it, to increase somewhat the error. But of course, it is probable that only one of them are correct. Yeah, it cannot be that both of them are correct. But to be honest, I don't see where the problem is coming from. And I can't sleep very well because it is really, for me, a comparison of QCD with QCD. And even this 2.1 sigma for the whole AMU or 3.7 sigma for the window variable is really worrisome.
Yeah, well, thank you very much for that. Just to make sure that, but methodologically, you don't expect it to be wrong. I mean, they're just taking R ratio literally from experiment and then integrating that. That's what they're doing, correct?
That's what they are doing, yeah.
Did
I answer your question?
Yes, you did. Thank you.
Thank you. Thank you.
Let's take a question from Glennis now.
Well, first, let me just thank you, Zoltan. It was a beautiful talk, and you explained everything so beautifully. And then congratulations and thank you for the magnificent work, which is just phenomenal. The question I had was very similar, maybe a little more detailed than Gregory's. you even hinted at it at the beginning, because getting an absolute normalization in any experiment can be really tricky. And so a place that would pop to my mind is just one or all of the experiments has a tiny mistake in their calculation of the hadronic cross-section relative to the muons, right? You're trying to take this ratio, they have to have it to tremendous. Well, what precision, what sign, you must have tried this, like dropping out, for instance, if you drop out one or the other of Chloe and Babar, does one of them give you the answer that agrees? Or if you take the one that makes the answer most like yours, how much would you have to shift that? How, in other words, how big a systematic would it have to be relative to how big they think their systematic is?
So the answer is yes. I tried that. I did on my own the Babar and the Chloe, and the Babar is larger than the Chloe.
Do you want it to be larger or smaller? I didn't
What's
get
that?
the sign. I didn't assimilate the sign of the correction you need in R.
In this picture, you need larger R ratios to have larger A mu.
Okay.
Yeah,
Okay.
because
Okay,
that
perfect.
way are you approaching the experimental result.
Okay, so it's useful.
So in that sense, Babar is closer to the. So if you plug Babar into the R ratio method, then you get closer to the.
How much? And so if you dropped the ones that are not so close and said, okay, let's just use Babar, where would you? How much closer would it bring you? Is it just a little bit, or is it? If it gets you halfway or something, then you know.
So the difference between Babar and Chloe within these regions, 600 and 900, if I remember correctly, the shift is about 10. So from here, 18.2, you will be at 19.2.
Okay.
If I remember correctly. Yeah.
Well, that
So
was
something
really,
is 10 units of shift.
okay. Okay.
In 10 to the minus 10 units, this is here 10 to the minus 9.
Okay. Okay. Perfect. I did have one other question, which you can refuse to answer, which was it an accident that your paper and the G-2 announcement happened on the same day?
No, it is not an accident. I think nature wanted to do that, to have the largest height around it, but it was not my decision. So it was.
But it's nice. It was nice.
They did it in this way, and it was interesting. So
Yeah.
Okay. They wanted to actually, just an anecdote to that, they wanted to put us onto the cover page. We even had the cover page, but then they decided it is better to have it on the same day than having it on the cover page, because the cover page production was already proceeding faster. So it is not on the cover page, but it was on the same day.
It was very nice for physics to get that much profile in the press. And so, that was a good idea. Okay,
Yeah.
thanks a lot.
Yeah. Did I answer your question?
Yes, absolutely. Wonderful.
Okay.
Thank you.
Let's take a question from Kobe.
Yeah, I have a question which is not directly related to your calculation, but I think it's important. I mean, do you argue that lattice can reproduce the experimental result for the magnetic moment of the proton and of the neutron?
Well, that I don't know. We calculated it for the muon.
Well,
So
I know, but I mean, in fact, I think that usually they only calculate the difference between them, and there is no good agreement with the experiment for just the proton. Now, it is related, because if you follow the way that they extract the result for the muon, they do measure the magnetic moment of the proton in a hydrogen and without a hydrogen, and the ratio between them is a factor that enters the determination of A-2. So I just wonder if well, of course, you can take the experimental result. You don't need theory for that. But I mean, if you cannot trust that lattice can reproduce this basic quantity of the magnetic moment of the proton, why should we trust the lattice in general for this kind of experiments?
Well, you don't need to. So if you don't want to trust it, don't do it. It is, of course, not the same as doing analytic calculations. You can do an analytic calculation in a relatively short time, but calculating the same thing, just using a different here, just using a different action, as I showed you here. Here, these are two actions. It's a multi-year project.
Okay, thank you.
So you might trust it, you might not, but we cannot do too many things, and you have to select very carefully which problems you want to attack.
Well, I'm just asking whether you don't think that it's an important challenge for Lattice to really reproduce the magnetic moment of the proton.
Yeah.
Okay.
Yeah, I actually had a quick question, but maybe it's been answered already. So you show that the discrepancy was largest in this window function observable, which is also the nicest to calculate in some way. But that corresponded to some region in T. So does that have a mapping to a region in center of mass energy for the R ratio?
Very good question, and the answer is no. So you need the whole R ratio, not everywhere the same strength or same weight, but you need the R ratio for the whole region. And actually, we have now a project which tries to pin down or tries to give a numerical answer, a quantitative answer to your question. So qualitatively, you need the whole energy range. So it's hard to pin down the energy range, but quantitatively, of course, some of them are more important than the other. And we are trying to figure it out and do this calculation to get the most amount of information on these energy range, which we might be or should be focusing on.
Thank you. Any other questions?
Was that your question, or?
That was my question. Thank you. Yeah, I'm curious to see the final result. It looks like the difference there is large.
But I do not expect too much, to be honest, because you need the whole range. Yeah. But we will see the quantitative. It's a quantitative question, so you have to give a quantitative answer.
Okay. Any more questions for Zoltan? Okay, if not, let's.
I'd ask one if I don't want to,
Glennis, go ahead. Go ahead.
So coming back to the eta prime and the eta, it seems like, I have no reason to doubt your results, but I think it would be very impressive to demonstrate using lattice QCD that can be done precisely, because the vacuum quantum numbers really make it much harder, I would think.
Oh, absolutely, absolutely.
So,
but other groups have done that, and they had nice agreement with the experiment. So.
Okay. I thought they were pretty big error bars, was my recollection.
Yeah, it picked a big error bars. So that's what you called a little bit of cheating, while you're determining those quantities which have small error bars. But
well, you use the things like the pi and the k, which do involve, at least the pi involves light quark masses, but you don't make yourself calculate it because you use that to fit. So the eta and the eta prime seem natural. And as you say, it's harder with more quarks. So it seems like a very natural place to try to get.
yeah, I do agree. I do agree. So we have so many questions, interesting questions in physics, and
no, I understand.
It's a good one. It's a good one.
Yeah,
it's a good question. Yeah.
If you had a little extra computer hours, you could run that down.
Yeah, I do not have any extra.
What are your next projects?
Well, we want to improve in these results because, as we have seen, it is not decisive now, and it's something which really in the very focus of the interest of the community. Right. So my goal would be to reduce here the errors by a factor of 2, which means not just an incremental improvement. It is a real decisive factor if it is 5 sigma or not. So
Right.
it can easily move down a bit and get in contradiction with that. So anything can happen.
So your plot suggested that it's the finite size limit that you have to work on. Is that right?
Right now, the finite size is subdominant. That's the second largest error.
I meant continuum, right?
The
Sorry.
continuum is the dominant
Yep,
now,
I meant that, sorry.
which
So,
can be solved by taking a smaller lattice spacing.
and so that's in a way a brute force method. Is that more or less the only option?
I am not aware of any other method to reduce the error due to the continuum extrapolation other than moving closer to the continuum.
Right.
Yeah. So,
So how-
it's always like that. Whenever
Yeah,
you
yeah.
extrapolate,
Sure.
it's
So how
it's
much more, how much longer does it take if you if you got the lattice spacing small enough that you could reduce that error by a factor of 2?
So it goes by, of course, it goes by a squared because of the discretization scheme. So that means if you want to reduce it by a factor of 2, then you have to take a lattice spacing which is 70% of the original lattice spacing, and that can be usually it's like the next lattice spacings is as expensive as everything before.
Mhm.
So that's a rule of thumb.
Mhm.
Can be a factor of 2 or 3 off.
Well, with this writing on it, it seems like you should be able to get good grants for computer time.
Can I ask one question about your extrapolation?
Say it again.
Can I ask a question about your extrapolation? Can you go back to the plot where you have your extrapolation? You were just showing it a second ago.
Is what you mean?
No, the one that showed the. Well, I mean, this is kind of showing it, but.
For
there
the
was-
window function, you mean this one.
Yeah.
Okay.
So this one down here in the lower right-hand corner, right?
Mhm.
Yes. So
Bottom left.
bottom left. Thank you. So it looks like the value that you get is higher than sort of most of your low short distance values. And so it's something about your extrapolation which is causing it to kind of bend up at that lowest value, which I can see in the fit with no improvement. It's very clear that there's that.
This one.
Yeah, that one. So with no improvement, it's very clear that there's sort of that, upward motion as you're extrapolating to small distances. But with the improved one, it's pretty flat. And except for that last point, everything sort of seems to be trending down. But then your extrapolation is a little bit higher. And I understand that it's not that big and it's small compared to the separation between two. But can you explain how that comes about, why the extrapolation tends to bring things up there at the bottom?
Okay.
Am I making sense?
So absolutely. So first of all, there is no way that you can bring these points down to that value.
Oh yeah, no, that seems clear.
That's
clear.
the basic starting point.
Yeah.
But wait, can I just clarify something? Maybe Neil and I are confused, or Neil's confused and I'm not, or some combination. I thought this comparison was merely a methodological check to make sure that the discrepancies with the data-driven method weren't a result of some problematic region for the lattice. But you still have to use the thing you call no improvement in your calculation. Isn't that right?
You say that I should use all the time no improvement, or?
No, I'm trying to ask, so restricting the window function.
Yes.
Somehow I got the impression, I didn't mean to interrupt Neil, but I knew I have, so I'll keep going. I had the impression that the function of that restriction in your window
Yes.
was to give you a very robust comparison to the data-driven method, which allows you to make sure that it's not some particular region of lattice vulnerability, which is generating the difference. I mean, if it is, fine. But anyway, you wanted to isolate what part of the lattice analysis in the region that's most robust, which is this window function region. There's still a discrepancy if you restrict both to that region. But am I right that to actually calculate G-2, you need the entire region?
Absolutely.
Yeah.
Absolutely.
But I guess the point then is that that value at the low is actually the no improvement extrapolation. The dot with the error bars that's labeled BMW-C20. That's the, I should see that as the extrapolation of the no improvement. No, on the left-hand side. On the left-hand side.
So on the left-hand side, this is these 208. Yeah, you see, this is almost 208, and this is the 208. Yeah.
Yeah.
So this value is the value here on the left-hand side, extrapolated to zero lattice spacing.
But it's the extrapolation of the no improvement or the extrapolation of the SRHO improvement?
With improvement and without improvement, all of them. That's why I said that's hundreds of thousands of ways to extrapolate to the continuum. And what is really worrisome, what I really cannot really sleep well, that these numbers, yeah, as you say, they are relatively flat, not really flat, a little bit of a curvature, but I just cannot imagine how to bring it down to 200.
Yeah.
I don't see any way to bring it down to 200.
Right,
And
so the other has to come up.
What's that?
So the conclusion is the other has to come up. But just to be sure that we're understanding, you say you're very persuasive, Zoltan, but to be sure that we're understanding properly, the thing labeled SRHO improvement, would you please go over again? It's not like it would be kind of misleading if that was your terminology for restricting to the window function. So
this SRHO improvement is just one of the improvements we have used. Yeah. And this is improving the observables. So nobody's using unimproved lattice anymore. So you improve the action. So for instance, in our case, we had the following improvements. We had a semantic improvement in the gauge action, a 3-level semantic improvement. We had a stout improvement in the four levels of stout improvement to reduce the pion tower. And in one case, that was the finite volume case, then we have 4 hex improvement, whatever they mean. Yeah. And you can improve on the action level, and you can improve on the observable level. And that's how these observable was a little bit improved. That means that you cannot improve it 100%. So it will be not a completely fat, and no cutoff effect will be there, but you can remove a large fraction of the cutoff effects. And what you see here is no improvement. There is a slight cutoff effect, but not too much. Yeah, a few percent. Yeah? And these few percent can be even further reduced. But whatever we do, we always have these numbers, which are certainly above the 200, which is the R ratio. Actually, there are papers, of course, to do that. That's what I said with the luminosity measurement, and I simply don't know. I don't know. Of course, it can be that we made some mistake. It was a terribly large work. So it's really, in a very dense way, it is 130 pages. So it can be that we made something wrong. We had a mistake in it. And that's why we are eagerly waiting for other groups coming out, at least with the window, because the window is cheap. both from the manpower point of view and from the computational cost point of view.
Okay, Zoltan, thank you so much. I'm going to stop the recording here. We can keep discussing, but yeah, thank you for a great overview of
Okay, sure. Did I answer your questions?
Absolutely, yeah, absolutely. Yeah, that was great. Thank you.